Hey Wheat North, Mr. Yurgo here. This video is going to get into enthalpy and calorimetry. We've already talked about calorimetry a little bit, so we'll focus on enthalpy because that's where we're going to be kind of spending a lot of time. Enthalpy is referred to as delta H. We use the symbol H for enthalpy. And we've kind of also used this term, the heat of the reaction, and these, for our purposes, the enthalpy and the heat of the reaction are going to be pretty much synonymous terms. Now, the enthalpy, the change in enthalpy, is the difference between the products where you end up and the reactants where you start. And what I'm talking about there is the bond energy, or the energy kind of stored in the bonds, right? The bonds have potential energy stored within them. We've seen diagrams like this before. When two atoms come together, that actually releases energy because they're reaching a more stable, lower potential energy state, right? And if you compare these two graphs, they're kind of showing the same thing. Carbon dioxide, remember, has double bonds. The formation of those bonds has released a lot of energy. Meanwhile, oxygen also is low in energy, but not as low as carbon dioxide is. And so when you break these bonds, which was going to require energy, you're going to have to input energy into the system in order to break those bonds, to overcome that Coulombic attraction. And then you have like an intermediate state, and then they form the carbon dioxide. They're going to release energy in the process. And so that's where this energy is coming from. So if your products have lower energy than your reactants, then it's exothermic. If it's the reverse, if your products are higher in energy, then that means we had to input some energy in order to get there. That's going to be endothermic. And here I need to kind of clarify something, because in biology you talk about breaking of bonds as releasing energy, right? Through cellular respiration and glycolysis, we break the bonds in sugar, we use some oxygen, and that releases energy, and then we use that energy to make ATP and so forth. That's actually not true. It's not fully true. It does release energy to convert sugar to carbon dioxide and water, but it's not because you're breaking the bonds. The breaking of the bonds requires energy, right? Otherwise, why would the sugar even exist in the first place at all? Why wouldn't it just, if it releases energy, then why wouldn't it just convert to carbon dioxide and water on its own? We have to input energy. We have to get up into a transitional state to break those bonds and separate those atoms so that they can recombine and release energy in the production of water and carbon dioxide. So breaking bonds, I want to really emphasize this, breaking bonds requires energy. You have to add energy to break bonds. Forming new bonds releases energy. And in this case, in this example, we happen to be releasing more energy than we're overall inputting. And that's because water and carbon dioxide have a really low potential energy if you had their bond energy diagram. But it's not the case that breaking of the bonds in the sugar releases energy. It's just that we release energy when we form the bonds. But in biology, you kind of ignore that part. You just kind of like gloss over that. But that's a very common misconception to think that breaking bonds releases energy. Breaking bonds needs energy. You have to separate those atoms from each other in order to break bonds. So the enthalpy is the heat content of the system. And we can't actually measure that directly. We can only measure the change in an enthalpy. Here's a formula that we'll use a lot. This is kind of by definition what enthalpy is. It's the energy of the system plus any work that's done. So in scenarios where we don't have a change in volume, meaning we have a rigid container, or there's no gas produced or consumed, or we have gases that are being consumed and produced, but we have the same moles of gas on both sides. If the volume isn't changing, then there is no work, right? The only work that we're going to talk about is when there's an expansion of a gas or the compression of a gas. And so if those are zero, then enthalpy essentially is Q. So in all aqueous solutions, in all aqueous reactions, enthalpy is going to be equal to the heat. There's lots of different types of enthalpies. We can talk about the enthalpy of a reaction, where we have delta H and we put this little Rxn, and if it's positive, then it's endothermic, where it's absorbing energy. If it's negative, it's exothermic. And we can have enthalpy of vaporization. This would be converting liquid to gas. Enthalpy of fusion is kind of similar, but solid to liquid, so just melting ice. The energy required to melt ice into water is 6.01 kilojoules for every mole of water. We can also have enthalpy of formation. We'll use these ones a lot, actually. Put a star next to this one. This is always written in a way that produces 1 mole of product, and starting with the elements in their most natural, most common state. So diatomic hydrogen, diatomic oxygen. You'll see a lot of fractions with this because it's it's written in a way that it produces only 1 mole of product. And then enthalpy of combustion is another one. It's really just another enthalpy of a reaction, but because it's so common, we kind of give it its own name. Notice the fractions as well. This is written in a way that we have our carbon-hydrogen compound written with 1 mole, and so we sometimes need 13 halves of oxygen molecules, for example. Now we can manipulate this delta H. It's an extensive property, which means it depends on the amount. So the more gas you burn, the more heat you release, right? The more sugar you oxidize, the more energy you release. So that's kind of common sense. It depends on how much you have. A lot of times we'll be switching equations from how it's written in the forward way to like the reverse way, and if you do that, you have to reverse the sign on the delta H. If it's endothermic going to the products, then it's going to be exothermic going back to the reactants. If we need to take a reaction times 2, for example, or times a half, we'll do this when we start talking about Hess's law a lot, then you have to do the exact same function to the delta H. So this is kind of connected to the extensive property point. If you do the reaction twice, you're going to produce twice the heat. So here's a couple examples. So we have carbon and oxygen producing carbon dioxide. It's endothermic, but if we reverse the reaction, then it becomes exothermic. Notice that it's the same quantity, it's just we've just flipped the sign. If we have 12 grams of carbon, that's 1 mole, and so that's going to be 393.5 kilojoules. If we have half as much carbon, we're going to produce or require half as much energy. Same thing here. If it's written in moles, if we have 1/10 of a mole, it's going to be a tenth of the energy. A couple other side notes. Delta H depends on the state of the substances. So if we're forming water as a gas, that's different from if we're forming water as a liquid. They require different amounts of energy. You also need to get used to fractions. Like, let's say we have this example, the production of ammonia. This is the Haber process. And if we want to write a thermochemical reaction for this, for the formation of ammonia, that's always written for the formation of 1 mole. We're going to have to use fractions. And we'd have to take the delta H divided by 2 as well. All right, calorimetry. You've seen these before. We're going to use a coffee cup calorimeter in a lab to kind of track enthalpy changes. And again, you can't measure enthalpy directly. You can't measure like the internal internal energy of a system. You can only measure how much it gives off or how much it absorbs. So we use calorimetry to do that. For our purposes, we're going to assume that the calorimeter is a closed system and it's insulated. We know that that's actually not true fully, but we try and do the best we can by adding a couple layers of styrofoam and covering it and so forth. So that's a quick overview on enthalpy and calorimetry. We'll get into enthalpy especially a lot more as we start talking about Hess's law. If you have any questions, as always, write them down, bring them up in class. Otherwise, this is Mr. Yergler signing off.